Welcome back to finite element methods, where in this videos we will continue our discussions on the constant strain triangle elements, where specifically we will look at two models that can be used in solving a structural problem, and we applied it in the finite element methods. Most of the engineering problems that we may solve in our real life or real applications will be in 3D, but not all cases are required to be solved in 3D. So in this lecture, we will look at models that can be used to deal with this kind of problem, and also to see under what conditions we can apply them. So the first model that we are going to consider, which is known as the plane stress model. So this model is a state of stress in which the normal and shear stresses in the direction perpendicular to the plane of the body are zero. So if, for example, I take xy plane is a plane of the body, so if I take these x and y as the planes of my structures, so this is my structures, then the one that is perpendicular to this plane, which is in the z directions or in the thickness directions, then as stated in these statements, the only non-zero stresses are in the form of shear normal stress in the x and y directions, and also the shear stress on these xy planes. However, the zero stresses are the one that is acting in the thickness directions or z direction, which is here we have three terms with zero stresses value, which is normal stress in z directions, the shear stress in xz and yz directions. When solving structural problem, it is very important to analyze how the geometry of our structure looks like, and also what kind of loading applied to the structure. For the plane stress model, usually this model is only valid to the thin structure, such as flat plates subjected to in-plane loading, or we have thin discs under pressures or centrifugal loading, such as a pressure vessel, maybe in a kind of aircraft body, or also known as a fuselage, or space habitat skin, which is the skin usually having a very thin structure or in terms of its thickness. The second model, which is known as the plane strains, so this model is a state of strain in which normal and shear strain in the directions perpendicular to the plane of the bodies are zero. So if the xy plane is a plane of body, then the non-zero strains are we have the normal strain in xy directions, and also the shear strains on this xy plane. However, the zero strain, which is the strain that is in the thickness directions, we have normal strain in the z directions, we have the shear strain, which is in the x, z and y, z direction. So if we look at this figure here, we have a dam which is subjected to pressure, which is came from the water, and the plane of the body, which is the xy plane, then the thickness which is in the z directions. So the plane strain condition usually used for long and constant cross sections structures such as structural beams, for example a solid propellant rocket, and also dams. So in this solid propellant rocket, if we can imagine, so we have a propellant that we place in the solid in the rocket barrel. So we put, and usually this will create a high pressure inside this barrel. So the barrel itself is not that thin, but this pressure actually applied along these sections of this rocket body, and this can be falls under the plane strain conditions. As usual, once we have solved the system of linear equation in the form of kq equal to f, we actually obtain what is happening in terms of the translations or deformations that apply at each another points within our CST element. But sometimes we are also interested to determine what is happening at an arbitrary point or anywhere within our CST elements. So in this case, the field displacements equations can be used. So the displacements u and v at any point within the elements can be obtained by using the field displacement equations. But as we can see here, for one field displacements require us to supply three displacements a value that obtained from the system of linear equations. So that means we have to solve the system of linear equation first, then we can obtain the field displacement u and v anywhere within our CST elements. Where in this field displacement equation we have n1, n2, and n3, which is these three terms are known as the shape functions, and given by n1 equal to z, n2 equal to eta, and n3 equal to 1 minus z minus eta, which is z and eta here are the natural coordinates. Substituting n1 equal to z, n2 equal to eta, and n3 equal to 1 minus z minus eta into these field displacement equations, we get a new expression which is now written in the natural coordinate system for the u and v. But at this stage we still do not know what is the value of z and eta to be substituted in these two equations. The coordinate of particular point can be expressed in terms of the nodal coordinate systems. So for example here, for one CST element, usually we know the coordinate at each nodal point, and we usually know the coordinate of the point of interest where we would like to determine their displacements, and also maybe the stress and strain within our CST element. So in this case, we know at least the coordinate at 4 points. So if the point there, which is known as u and v, where we know the coordinates here, which is x and y, and x1, which is referred to the coordinate at point number 1, x2, y2 refer to the coordinate at point number 2, and x3, y3 refers to the coordinate at point number 3. So if we substitute this coordinate system into the field displacement equation, then we work as shown in this slide here, then we simplify this equation, then we are likely have two equation with two unknown, which is z and eta, as shown at the bottom of this slide. So with the two equations and two unknown, we can solve these equations. This is a kind of system of linear equation as well. So we can solve for the unknown, which is our z and eta. So z and eta can be obtained by solving the system of linear equation of these two set of equations. So this example actually shows how we can determine the shape functions n1, n2, and n3, and also the value for the z and eta out of one single element, where the point P is given as shown here. So substituting the coordinates value for each nodal point and also at point P in the field displacement equations, then we can rewrite these field displacements in terms of the Cartesian coordinate system as shown by the first two equations there. So the similar equations can also be rewritten in the as a functions of the natural coordinate system, which is given by the two equations as shown at the bottom of this slide here. Applying that, we know that n1 equal to z, and n2 equal to eta, and we know that n3 equal to 1 minus z minus eta. So substituting these three information into the first equation, then we can write the field displacement equations as a functions of the z and eta as shown here. Once we simplify the field displacement equations written in the natural coordinate system, then we have a set of equations with the two unknowns. So from there we can solve these equations by solving the system of linear equations. Then we can obtain here that z which is equal to 0.3 and eta here equal to 0.2. So this two value is actually refers to the conditions for point P, which is located at this coordinate system. So if, for example, I have point Q, which is located somewhere there, where is xy coordinate system, which is now different to the one that I have there. So maybe the term z and eta will be different from the one that we have for point P. So again, we substitute this z and eta into the n1, n2, and n3, give us these three value for this for the shape functions. In this subtopic 6.3, we will look at how we can derive the element stiffness metric for the CST element. So the element stiffness metric is again derived from the potential energy approach. Will be discussed in these lectures. where the element stiffness metric can be obtained from the energy equations in this potential energy equation, where the strength energy equation is given by the first equation in the slide, where this strength equation is equal to strain displacement matrix multiplied by displacement at the known nodal point. So substituting this the strain or epsilon into the strength energy equation, then we can rewrite a new equation which is given by the second equation in this slide. We know that for one CST element we have 6 degrees of freedom, so Q actually refers to the displacement at each nodal point both in x and y directions, where D, which is the materials matrix, which is the matrix that contains all the materials properties of our structures. So as we discussed before, that there are 2 conditions may involve depending on the geometry of the structure and also the loading conditions, which is the plane stress conditions and also the plane strain conditions. The B metric is known as the strain displacement metric, which is a metric that contains the geometrical informations of our CST element. T is the thickness of the plate, J is the Jacobian matrix, and the determinants of J is actually refers to the determinants of our Jacobian matrix, and it is given by the cross products between these matrix elements. So substituting all of this into the internal strength energy of the potential energy equation, then we have the first expressions or equations in our slide. And since we know the integrations of the small elements of the area, it can also be refers to the AE, which is the area of element, and can be substituted into this the first equation, then give the second equations in the slide, where we know that the area of our CST elements can be obtained from this half of the determinants of our J matrix. Then if we solve this internal strain energy, then we can obtain the stiffness metric for our CST element, which is given by these expressions. So in this example, we'll actually demonstrate how we can determine the stiffness metric for one CST element as shown in this figure, so which is the same elements as we used in the previous example, where we are required to determine the value for the shape functions n1, n2, and n3, and also the coordinates, natural coordinate z and eta, which is to be used in our problems. But in this problem, the thickness of the element is given by 1 millimeter. The modulus of elasticity, which is given as 73 gigapascal, and the Poisson ratio, which is given by 0.3. So to obtain the stiffness metric for one CST elements, which is we have to do, as I mentioned in the previous video, this process is a very tedious process, and the similar equations for this stiffness metric can be obtained by solving these equations directly. So this equation that we have in this slide, which is actually equivalent to these equations. If I skip this part as shown in this lecture notes, this part as well and this part as well, but instead of using these calculations, but I replace my calculations as shown by the equations in these slides. So if, for example, if I substitute the coordinate at each nodal point, which is as given by these three coordinates in x and y Cartesian coordinate systems, into this K matrix for the CST, which is I have set up in my Excel here. So if I substitute all these x and y coordinate for each nodal point, which is in this case given by 1.5 and 2 for the nodes number 1, and 7 and 3.5 for the nodes number 2, and for the nodes number 3 is reside at 4 and 7. So with all the equations, in the first row and the first column here has been set up in my Excel. So by substituting this coordinate at 3 points, then I can get this value here, which is this value, which is equivalent to the one that we get in the lecture note, these numbers here. So we have this number correct, this number correct. This number here should be -2834 instead of 2.409, and all the numbers here, as you can see here, are correctly calculated at each address in our K matrix. So now let's look at the first vector, which is at this stage we should be able to construct the K global for each CST element. Then in solving the system of a linear equation, the others known information which came from the first vectors. So we will consider the effects of the body force acting within the elements, and also the traction force acting on one of the edge of the elements in our topics here. First, let we look at the body force. Suppose components of body force, which is given by Fx and Fy, which is the body force may act in both directions, x and y axis, act at the centroid of our CST element, which is as shown here. So since we have the body force which is acting at the centroid of our CST element, then it is very important now to transfer this body force into the what we call it as the equivalence force that acting at each nodal point. So since we have 3 nodal points, so the body force here will be divided by 3. For the traction force, suppose a linear varying traction force acts along the edge of 1 and 2 of our CST element. So we have CST element, and assuming that we have a traction force which is spanning from point number 1 to point number 2 on our CST element. And in this case, as we can see here, this traction force is having the bigger traction force which is given by T2 at node number 2, and slightly lower traction force at node number 1, which is given by T1. And this traction force is inclined to a certain angle theta, which is measured from the horizontal axis here. So in this case, with our traction force that is inclined to a certain angle, then we first should explode this traction force into the x components of this force and y components of this traction force. So when we have exploded into the x and y components of traction force, then we can now write the equivalence nodal force from this traction force, then transfer it into the nodal point as well, as shown in this slide. And this can be done by solving the first equation that we have in this slide. In some cases where we have the traction force which is uniform, so the traction force at both point number 1 and point number 2 will have the same magnitudes. So in this case, the Tx1 will be equal to Tx2, then this can be called Tx. Similarly to the Ty1, which is equal to Ty2, then we can call it as Ty only. Thus, this equation here again must be somehow transferred into the equivalence nodal force vector both in the x and y direction, acting at the nodes number 1 and nodes number 2 by distributing it equivalently in both directions by solving these equations. So to demonstrate how we can deal with this traction force or distributed force, so let's look at the examples. So in this example, we have a two-dimensional plates which in the shape as we have here. Then we are asked in this example to determine the equivalence points lobes at nodes number 7, 8 and 9, where we have the traction force spanning on these edges 7, 8 and 8, 9. The magnitude of this traction force is 2 kilonewton per meter square. So as we know that this traction force is actually acting on the surface of our plates. Other than this traction force, we have another force which is in the form of a point load applied at nodes number 9 with a magnitude of 3 kilonewtons applied vertically at nodes number 9 and pushing this number 9 downwards. Before we begin, I think it is better to label the nodes numbering for each nodes that we have in our structure. So node number 1 start here, number 2, 3, 4 we have node number 5, and nodes number 6 here, nodes number 7, 8 and 9. So we know that at each nodal point we have 2 degrees of freedom. If we are talking about the displacement, then we will have displacement Q1 and Q2 at nodes number 1. So similarly for the force, we can view the force in a similar way as we view the deformation as well. So the force can be written as F1 and F2 at nodes number 1, but at this point here there's no load, applied load exists, so F1 and F2 is equal to 0. So the most important part in our structure here, which is on the edge 7, 8, 9, where we have the 2 type of load apply on these edges and on this nodal point. So to view this similar to the degrees of freedom that we discussed just now, so we can actually draw the line number 7, 8 and 9 as shown on the figures on the right here, and we label all the forces in the x and y direction as shown here with their indices as well. In terms of geometry, the coordinate at nodes number 7, 8, 9 is given in this slide, where as we can see here, the vertical distance from point number 8 to point number 9, which is equal to 20 millimeter in this case, and the horizontal distance, which is equal to 15. So we have 100 minus 18, so we have 15 millimeters in terms of the horizontal distance, and vertical distance we have 20 millimeters. So with these unknowns, the horizontal and vertical distance, then we can use this information actually to determine the angle theta for this edge number 7 and 8. So for the angle theta, we can use the sine rule or cos rule to determine the angle. So if we take the cos theta of 20 over 25, then this is actually equivalent to 4 over 5, and the sine theta of 15 over 25, this is equivalent to 3 over 5. And since our attraction force are inclined to the angle theta, then we first must to explode this force into the x components and y components of this attraction force at point number 7 and point number 9. And this can be done by taking Tx equal to T cos theta, which is will give us 1.6 Newton per millimeter, and Ty equal to T sin theta, and gives us 1.2 Newtons per millimeter. So the length of this edge, let's say we take here as the nodes number 7 and nodes number 8. So the length of edge 7 and 8 can be obtained from this simple trigonometric rule, which is if we take the L here, which is equal to the square of 15 plus square of 20, and we square root everything, then we get the length of this edge here, which is given by 25, and also given that the thickness of our plate is 10 millimeter. Since the traction force that we deal with, which is in the form of a uniform traction force, so these equations will be used to transfer our traction force into the its equivalent nodal force at each nodal point, as shown in this figure, where we know the thickness of our structures, we know the length of the edge where we have the traction force acting on it, and then we divide it by 2 and apply to each nodal point, nodes number 1 and nodes number 2. Substituting all these information that we have calculated earlier into the equation, then we found that the equivalent force at nodes number 1 in so this is for nodes number 1 in x directions and in the y directions, and similarly for the nodes number 2 in the x directions and in the y direction as well, which is given by this value. So this is the equivalent force contributed from the uniform traction force of 2 kilonewton per meter square applied on the edge 7, 8. Similar process applied to the edge 8 and 9, which in this case, since the edge 8 and 9 having the same slopes and the same the horizontal and vertical geometry as edge 7 and 8, so the length of this edge 7 and 8, which is also equal to 25, while the thickness is remain the same, which is 10 millimeter. So substituting this into the equivalence of force applied at each node for the edge and 9, then again we get this the same numbers which is applied to the edge 8 and 9. So which is the two value here, which is will be applied on the nodes number 8 in the x and y direction, and the other two here, which is will be applied to the nodes number 9, which is again both in the x and y direction, which is all the numbers here is written in the transpose formats of the vector. So from the calculated equivalent nodal forces applied on the nodes 7 and 8, so we have these 4 values of forces in x and y directions, and similarly on the edge 7 and 8 and 9 we have these 4 forces again applied in the x and y direction. Since from that we can see here we have at point number 8 where we have the value that is calculated twice, which is the first we calculated on the edge 7 and 8, then we calculated again on the 8 and 9. So in this case the two value must be added between these two values. So this is what we get or represented by F15, which is the force at node number 8 acting in the x directions, and F16, which is the force at nodes number 8 acting in the vertical direction, which is actually contributing from this the summation between the two. So we have 400 Newton, or equivalent to 0.4 kilonewton, and we have 300 newtons in the y direction, which is equivalent to the 0.3 kilonewtons as in this figure. So this is how we deal with the uniform traction force, and how we can transform it from this form of a pressure or distributed force into the equivalent nodal force at each nodal points. But there is one more force that we still didn't include at this stage, which is the point load that applied to the nodes number 9, which is we have a 3 kilonewton of force applied at node number 9, and it is applied in the vertical directions and pushing the point number 9 downwards. So now we are actually talking about this point load, which is we have to include it as well in our force calculations. So in this point force, then we have to add it to this force, which is the vertical force acting at nodes number 9. Then we add it with the 3000 Newton, with the negative sign here to show that this force is in the downwards direction. So if we add these two, then we get the force, or the vertical force at nodes number 9, which is represented by F18 here, which is equivalent to 2.89 negative kilonewtons, or we have 2.89, which is actually acting in this opposite direction to this arrow that we have for the F18. So that is how we should view and deal with this traction force when it is involved in this structural analysis and solved using the finite elements methods. So at this stage, actually we are actually ready to solve and to rewrite our system of linear equations and solve it simultaneously by using any system of linear equations solver for the unknown displacement at each nodal point Q. To help you master in these constant strain triangles problems, several assignments have been included in the UTM e-learning system. So I hope that every student can or should try to solve every problem supplied by using the CST equations supplied in the separate documents, which is these equations. Alright, thank you very much, and hope to see you in the next topic. Thank you.